Okay, so what is superconvergence? It's very fast training of neural network using large learning rate. And when we say very fast training, we are saying that instead of waiting for 200 epochs for networks like ImageNet, or waiting for, let's say, 100 epochs for a network like, or waiting for 100 epochs or to wait for CIFAR, we can train the complete CIFAR to 90% plus accuracy within 10 or 15 epochs also. Now, I've taken this abstract from the paper. It's a very beautiful paper. Please read if you get time. In this paper, we describe a phenomena which is called the superconvergence, where neural networks can be trained an order of magnitude faster than the standard training methods. The existence of superconvergence is relevant to understand why deep neural networks generalize very well. Now, this paper is written by Leslie Smith. I have a photograph of him later on also. There's a video which I've also added in the lecture notes. Take a look at that video. It's a 20-minute video. And read the paper. First of all, this paper is written in English, which means that when I say English, I'm making fun of the papers which are not. So you will be able to get a very good understanding of what is actually happening across different fields. And he has a comment on SGD as well, that why SGD is actually working the way it is. So pretty easy paper to read, not mathematically heavy as well. One of the key elements in superconvergence is training with a network with something called one cycle policy. We're going to see what this is, and a large maximum learning rate, right? So we're talking about maximum learning rate, which means we will have something like a minimum learning rate also. Now, the primary insight that follows superconvergence training is that the last learning rate regularizes the training, hence requiring a reduction of all forms of other regularization. And this is a very important thing. If we are using one cycle policy, not only it itself is going to act as a regularization for your model. Why do we use regularization? To not get stuck in minima, okay? And how do we know we are getting stuck in minima? For example, Prakash is getting stuck at 84. He is stuck at a specific minima. So if we use one cycle policy, first of all, we are not going to get stuck at these minima. Second, it is going to require a reduction of every single other kind of regularization as well. So if you're following up with, let's say, one cycle policy, you may not have to use a lot of image augmentation. You may not have to use, let's say, a lot of dropout, or even L1 or L2, or even weight decay. Right, so you can actually train your network much faster to a higher accuracy. And this higher accuracy, I don't mean that you're going to beat a state of art, but it's going to take you very close to the potential highest accuracy of your model, and that's how you use it. I'm going to explain it further. Now, before we understand what is superconvergence, let's look at the background of or how we have come to this particular point, or how Leslie Smith actually thought about targeting superconvergence. He's working on this field for quite some time. Now, history and the evolution simple learning rates to OCP, one cycle policy. In the last session, we worked on something like this. We took our network, we trained our network through some iterations, and we changed the learning rate slowly as we are moving through each iteration. One iteration is equal to one batch. So this image shows us going through 300 batches of our data set. Now, when we do that and we increase the learning rate, we are going to follow our loss curve, and we're going to see that it actually shows some minimas at some particular value. Wherever it shows the least value, at that value the loss was reducing the fastest, so we want to take that specific value, right? And sometimes your curve is going to look like this, so we like to actually smoothen the curve to get the proper value. Now, we are not going to spend a lot of time on this because this is something you're not going to use. For most of the networks, we already know the best learning rates. For example, the reason we use 0.01 for the CIFAR with SGD is because people have tried it out, they've tested it out, and that value is one of the best value. So we may not have to use it every time. Second, we have one cycle policy where we don't use this structure. We're going to use something else to find our learning rates. Third, if you're using your own data set, and that data set is very similar to, let's say, natural images or like ImageNet, you can still use the learning rate which are found there. So unless you have a very different data set, you may not have to repeat this exercise. Now, first change. So where are we right now? We are at a fixed, very good learning rate, right? For example, this in the last exercise also, you picked the best learning rate, and we were training our network for that learning rate. What is the first change we are going to do? We're going to add something called learning rate annealing. This is something we have discussed for quite some time. We have quite a bit of time we have discussed this particular part. Selecting a good learning rate is merely the first step. In order to efficiently train a robust model, we will need to gradually decrease the learning rate during our training. And the way we have understood this is by looking at our example of 0.3, 4, 5, 6, 7, 8, 9, and so on, right? So if our learning rate has allowed us to reach to 3, 4, 5 for a particular variable, the only way I can now fix 6, 7, 8, 9 is to reduce my learning rate by an order of 10. And that is why you most probably have seen that in the codes online also, we are reducing our learning rate by 10 times after every set of, let's say, 25 or 50 epochs. Now, it might be too large to converge. If the learning rate remains unchanged during the course of training, it might be too large to converge, which means our numbers are not able to become too small, which means the updates are still pretty big and we are stuck at some value. and we have to reduce our learning rate to fix that, and causes a lot of fluctuation to fluctuate around a local minimum. The approach is used to use a higher learning rate to quickly reach the region of the minima during the initial training stage and set a learning rate as minimum training process in order to explore deeper and more thoroughly in the region to find the minimum. How can we visualize what we have just read? Now, let us say this is an axis, and as we're going down, our value is reducing. So this is 0.3, this is 0.35, this is 0.3556, this is 0. So I'm drawing in, let's say, I'm drawing in a exponential or a logarithmic scale, okay? So this is 0.3, this is 0.35, this is 0.356, this is 0.3567, this is 0.35678, this is 0.35678 and 9, right? So we have these lines. I've drawn this in the, and in this, let us say our curve or the loss function looks like this, right? And the update which is coming back is in the order of 0.1, or let's say given smaller, let's say 0.01, which means I can be at this value 0.35, right? But next update comes in, it's going to send me to 0.36, which is going to be on top only. I can't go down, because if I want to go down on this curve, I have to use an update which is going to be on the 0.001 scale, but that update is not coming back to us because our learning rate is also pretty high, which means I'm going to be just traveling across or bouncing across this range. And because I'm bouncing across this range, I am not able to triple down, I'm not able to explore the deeper regions, I'm not able to explore the deeper and more thoroughly the regions to find the minima. So I'm not able to go deeper, because of which I'm not able to actually find the minima which is good for us. We are just stuck at some minima, and because of this 0.01, we are just going to be traversing there, and your loss curve is going to look like that. But the moment you drop it 10 times, now let's say I drop it to 10 times, my parameters which were getting stuck here now I can move to this line, and now I will be shuffling around this line, right? So that means my training curve is going to see slight jump. Now it's going to get stuck again. Now if I drop it 10 times again, I can start fixing this value, which means that from here where I was stuck, now I can triple down here, but now I'm going to be stuck here, right? So you see, we have to do this multiple times, and finally slowly after moving here and then here and then here and here, and I can reach here. So that is how we train, and we are going to slowly reduce our learning rate. So this is called learning rate annealing, that we reduce our learning rate as we are training our network more. There are multiple ways of doing this. First is called piecewise constant. This is something we saw last time, and I told you if you're doing something like this, then our meme is going to come in and is going to say that kabhi kabhi lagta hai apni bhagwan, right? For example, when you some error occurred in the video. No, my connection is live. And I'm streaming also.
Refreshing the page will solve the issue.
Yeah, refresh the page. Anup, just refresh the page on your side again. Okay, so piecewise constant. Piecewise constant would mean that we know that after 25 epochs we have to reduce our learning rate, and that's not the right strategy, because quite possible you are exploring even the upper ranges that I have not even come to this particular point, and you start reducing your learning rate, which means that now you're sending very small update, and I was stuck at, let's say, 0.25, and you have reduced the learning rate to a very small value. For example, you're at 0.001. Now imagine the number of updates I'll have to take from this guy to take my 0.25 to 0.3. It's going to take very long time. So we need to know precisely when we reduce it, and one way we can figure out is by looking at the loss curve. You see, the loss curve here is actually between two bounds here. I have this minimum line and I have this maximum line. So this is what you're going to be setting when you use your reduce alarm plateau. You set your lower bound and you set your higher bound, and using that, now I can come out. Now I can figure out when I have to reduce. So okay, benefit. As we've discussed, we're talking about the benefits of our annealing rate. As we've discussed through our through our variable value example, we say we evaluate at 0.3456, but if our updates are governed by minus gamma, this is learning rate, let's say, a delta L by delta partial derivative of loss with respect to the weight, we can only go up to as low as 0.001, which means I can only fix 0.345. To go and fix 6, 7, 8, 9, I'll have to reduce my learning rate with the order of magnitude 10 every time. Now the piecewise constant, we reduce the learning rate gradually. We keep it constant for a few blocks, We keep our learning rate constant for some epochs and then we drop it with a magnitude of 10 every 25 and 50 problem. But the problem is, again, this, right? That is what this link is going to open up. We should actually change the LR. When should we actually change the LR? The process is as follow. Assume that you know when to change and realize that you don't know shit. Then test multiple times and see what gives you best results, and then use that particular part. This process in the academy is called hyperparameter grid search, which means you're going to search at 25. First of all, you're going to run search at 25, then you're going to search at 35, then you're going to search at 45, and you're going to find a sweet spot where you should reduce it. After finding that sweet spot by using many searches or many different tests, right? You're seeing two axes here, x-axis and y-axis. X-axis might be epoch, right axis might be learning rate. So you're going to keep your learning rate constant, and you're going to change your number of epochs to see when exactly you should change, right? So this is something which is called hyperparameter grid search, which is literally the brute force search, which we don't want to follow. So we are going to follow a simple solution, which is called reduce LR on plateau. What is reduce LR on plateau? It is going to look that you're plateauing it, and then we simply change the learning rate when our loss itself is getting plateaued. Now in PyTorch, we have this thing built in, which is called torch.optim LR scheduler reduce LR on plateau, and we have some parameters there. I want to look at some of the parameters there. Optimizer, we are going to select an SGD for us. Mode, we are going to select one min or max. In the min mode, LR will be reduced when the quantity monitored had stopped decreasing, right? This is what we are interested in. We want our loss to reduce. Okay, factor. By what factor the learning rate should be reduced? This is by default is 0.1, which is like 10 times as we discussed. Patience. Number of epochs with no improvement, after which the learning rate will be reduced. For example, the patience 2, then we ignore the first epochs with no improvements, right? I also want to look at threshold. Threshold is the measuring for the new optimum to only focus on significant changes. For example, default 1 E4. Threshold mode. This is important. Now, one is relative and the other one is absolute. So you can select one of the relative or the absolute. Now, let's say we set a threshold of 0.001 in absolute. That means that if the value has changed by this amount, then you're going to change the LR. That is your threshold. But if you say relative, in relative, we can actually work with percentages. We can say if my loss is not changing by this percent, then reduce the LR. So both of them are very different. Both of them are very different in the way we calculate them. So I want you to think about. This is something I commented on the chat also in the Telegram also. I want you to think about that absolute versus relative. Which one should you use, and how should you set either of them? Because this is very important. I'm going to ask this as a question in the quiz also, that you're going to use the relative one or you're going to use the absolute one. Which one would you like to use? Okay, now this is the second change. So what is the second? What is the first change? First change is that we are going to anneal our network. We are going to anneal our learning rate. We are going to reduce it from a large value. But the second change we are going to do is reverse of this. The second change is warm-up strategy. Our variables are initialized randomly, right? So when we initialize the network is completely random in nature. Shouldn't we give our network some time to warm up, or to actually align with the variable in the, or align with the right direction before we actually train them? So I made a small image. I'm going to copy this image and explain. If we put threshold value, then we will have to use patient value also. Not necessary. All of these values have some default values, so you are going to use all of the values, but if you're not setting it up, there's going to be some default value which you will end up using. Here one. Please. Oh. Hang on. Okay. Now, so I'm going to refer to it. I drew it in the when I was making the content to help you understand. Okay, let us imagine imagine that I can take another example. Give me just 1 second. I want to search for a good image so you can build your intuition properly. Okay, I'm going to use this image in a second. But first, let me explain using the 2D image. Then we're going to go for 3D image. Okay. Okay. Now let us say that we want to end up here. We want to end up here, right? This is where our parameter wants to end up at, and let us say that this is where we are starting our journey. This is where we are, and this is a sort of valley between us, that I can't pass this valley, I have to go around. Now if I use a large learning rate, so first of all, our parameters are initialized randomly, and in the initial few cycles whatever updates which are going to come in, they are coming in a random order, right? Which means that I can actually think of it like exploration. That instead of actually going in a direction, we are actually exploring. All the variables are actually trying to go in random directions right now. That can be thought of as an exploration instead of going exactly where I want to go. Now, if I keep my updates which are coming back small, I can keep this exploration on in a region which is bounded nearby. But if I use a large learning rate from the beginning go, from the add go, then my backpropagation or my SGD is going to determine that's the direction I need to go in, right? And our variable is going to start going in this particular direction. Now imagine that our value was something like this, right? What is going to happen is that we are going to start going in this direction. We are going to start going in this direction. I'm going to now realize that I can't breeze through this mountain, so I'm going to reach here. Now where do I want to go? I want to go inside, right? I want to go like this, but I can't because there's a valley inside, and I have momentum also, which is going to just push me slightly here. Now I can't draw again this on top of it, so I'm going to draw this below it. So here I'll realize that okay, my gap has increased and the overall vector is in this direction, right? The overall vector is in this direction, so I'm going to now start my journey in this direction. The moment I reach, why will I reach here? Because of the momentum will push me to slightly farther distance. Now the moment I reach here, I'm going to realize I'm going to go in this direction. I have a vector in this direction, so I'm going to go back and forth and back and forth and back and forth, right? So on this one region itself, I'm going to stuck here, and I'm just going to keep on moving in this axis only. I will never be able to reach that point. However, if in the initial few parts, if the initial few sessions, I would have allowed some random motion, right? Quite possible. Is this guaranteed? This is definitely not guaranteed. Quite possible that I might have reached a particular point where I could have done this, right? So this is why I actually took this graph also. Now let us say that we are at this specific point, right? We are at this specific point. Let us say we are at this specific point, okay, and we want to be at this specific location. We want to go here. Let's say that is our minimum. Now if you look at what HGD is going to see, now you can see some depth here, right? HGD is going to see depth, right? HGD doesn't know direction of the where you want to end at. HGD is just going to see the depth. Where is the where is the steepest drop right now? Now if I actually want to go here, I have to go on top of the mountain, and then I have to travel down. But this part is really easier. But HGD is immediately going to push it on the downside, because that is where the steepest curve is right now. But if we allow some randomness to be there in the motion, or randomness to be there in the initial movement, my particles might actually come on top, and then I can actually take this particular way. So what happens when we are using smaller learning rate, when we are at the initial of the phase, when we are actually just starting a network, right? So when we are starting a network and we use a small learning rate, we allow this movement to happen. So there are two ways in which you can do it. We use a constant warm-up. That means the in constant warm-up, you train a model with a small learning rate for few epochs and then increase the learning rate to k times. So basically you have that step, right? So what is going to be constant warm-up? That we increase our learning rate slowly to this, right? You've done your exercise. In the exercise, you found out that you want to be at 0.0012. You figured this out, but you don't start this at the 0th epoch. So in the 0, 1, 2, 3, 4, 5, in 5 stages, you're going to change your values to reach that particular value, and you're going to start with a very small learning rate, something like this, right? And it can be order of magnitude smaller also. So we follow this particular part, and this is called the constant learning rate, because we're keeping a learning rate constant, again piecewise constant. Another would be, okay, what is this? This is this, that we are keeping our learning rate constant for some epochs. Another one is going to be the gradual learning rate. We actually change our learning rate every iteration or every epoch. So gradual warm-up, as the name suggests, you can start with a small learning rate and gradually increase it by a constant until you reach the k times the learning rate. Basically, till you reach the learning rate. This approach helps the model to perform better with huge batch sizes, which is in part with the training error of the trained model with a smaller batch size. Now, this is where Leslie Smith enters, right? This is guy. He's pretty old, but he's very intelligent. That's why I'm recommending to look at his video as well as his okay, if you put, okay, if fixed threshold say 0.0001 is used for reduce alarm factor, then also there might be a case the model gets stuck in low command where the expectation how to handle the other case. But in the so you have to have a limit on greed. Now the reason I'm saying this is because if you get stuck at 0.001, that means you did not get stuck at 0.1, 0.001, 0.001, 0.0001, right? You got stuck there. Of course, that is going to happen. So you are ultimately going to stuck somewhere. When it happens, when you get stuck there, again, go and change this value and now reset your model and train further from there. So you can always do that. But once you set this value, you can only reach that particular value. Okay, now this is Leslie Smith, and I was telling you that he has done great work on the superconvergence part. So please look at his paper. It's a very well written paper and very easy to understand also. So you introduce something called cyclic learning rate for training a neural network. What he saw is that first of all, we need to find a good learning rate, which is what we discussed in the last session also. We need to find a good learning rate, and then we are seeing we need to reduce the learning rate, and then we are seeing we have to increase the learning rate. So he came up with one strategy which is called one cycle, in which we are going to do both at the same time. So we are going to actually start at the low learning rate, right? So we discussed three things. First thing is that we first of all we have to find a very good learning rate. Then we said that we start at a small learning rate and reach that point. And then we also said that from here we actually drop down. We anneal a learning rate. This is one cycle. This is what Leslie Smith suggested that we do. And he wrote this paper called a cyclic learning rate, which came before one cycle policy. So in cyclic learning rate, what he did is he said that I don't want to keep on finding the values. What I'm going to do, so look at this particular paper. The essence of the learning rate policy comes from the observation that increasing the LR might have a short-term negative effect and yet achieve a long-term beneficial effect. Let's read this again. Increasing the LR might have a short-term negative effect, yet achieve a longer-term beneficial effect. This is what you observe. This observation leads to the idea of letting the LR vary between a range of values rather than adopting a stepwise fixed with exponentially increasing. So he said, instead of either doing this or either doing this, what he's going to do in case of the cyclic learning rate, we are right now understanding cyclic learning rate, then we're going to understand one cycle policy. So this was his first paper, which was cyclic learning rate. He said, I'm going to change my learning rate between two values, and I'll keep on changing my learning rate between them. This is what he recommended, right? And let's look at the image to understand what it means. Can somebody help me? No. Okay. Okay, so we have some parameters here which we need to take a look at. First is called cycle. Cycle would mean that how many iterations I have to run my network, and this is something which you identify. And second is step size. Step size is going to be what is the time or what is the number of iterations you're going to go from the minimum LR to the maximum LR. Generally, step size into 2 is going to be equal to a cycle. So that is what we are going to follow, but this can change. That is why we have to make a difference here. Then we have to find this max LR, and then we have to find this min LR. So these are some of the things which you have to find. Okay. Okay. Now let's see how do we calculate this, the complete sequence, right? Okay, I just want this to open up. Give me just 1 second. Okay, now I can directly write on this, but I have reduced options. It's still fine. Okay. So as I said, we have to find out this cycle, we have to find out the max LR, we have to find out this LR, and then this min LR, and we have to also find out our step size. Now let's see how do we calculate this. Cycle is going to be how many cycles are we going to run, right? Now, and we have to set cycle also, but before setting cycle, we set something called step size. So we have to define our step size. Let us say that our step size is going to be 300 batches, right? What we are saying is that I'm going to take 300 batches of data before I'm going to start reducing it. So I'm going to increase my learning rate from a min LR to max LR in 300 batches. After I read that, I'm going to take 300 batches further, then I'm going to reduce it to small, then increase, then small. So we have set our batch as our step size as 300. Let's give it 500. So I've set my batch as 500. So cycle parameter tells us in which cycle you are, right? So if I have done 500 batches twice, I would be in which cycle? I will be in second cycle then, right? If I'm not done with this, then I'm in the first cycle. So how do I calculate this? There's a simple way. I use a floor function. Floor is going to take the lower part of the integer. So floor of 1 plus iterations. Let's pick a number of iterations. Let's say I am on the 11,1111 iterations. And what is the step size? 2 into 500. So if this is the case, then this function is going to give us 1 plus 1000 divided by this is 1.111. So that gives us f of 2.111, and that tells us 2 cycle, which means you have finished 2 cycles. 1 cycle and 2 cycles. So, sorry, this means you are in the second cycle, right? I am at the 1111 iterations. 1000 iterations are done here. I must be somewhere here. So the cycle parameter helps us understand in which cycle we actually are. Okay. Now floor is going to reduce 2.3 to 2 and so on. Iteration represents the number of batches we have to complete. We have completed step size defined 1/2 of a cycle. Okay. So cycles is going to be, if you see, floor equal to 1 plus, let's say we are at these many iterations, and each step size is equal to 1000. So 1000 batches are required for us to go up, 1000 are required for us to go down. 2 into this is going to give us 1 cycle. So 10010 divided by 2 and plus 1 is going to be around floor 5 point something, and we get a 5th cycle, which means we are in the 5th cycle. Okay. Why is that required? Because I am going to use it for calculating my x. I'm going to see what my x is in a moment. So what is LRT? LRT is the learning rate right now, right? We are in an iteration of, let's say, 649. How do I know what learning rate I have to use? I have to look at my line, the minimum and the maximum, and I have to figure out exactly at what point I am. So this is that line, this is that calculation. So LR min. So LR min, I'm here. So I'm going to start with LR min plus LR min plus LR max. Now this 1 minus x can max go to 1. If it can go to 1, if the x is equal to 0, then I can go for LR min, LR max. That's a gap, right? This gap is equal to LR min and LR max, which means my line can from here go to this particular point. But I have this 1 minus x, which means I can now pick any point in between. I can pick all of these points. So I need to know what ratio of the cycle I am in. And how do we do that? We use this particular formula. We take the modulus of iteration divided by step size minus 2 cycle plus 1. Now this is easy to calculate. I don't want to spend a lot of time here. It's just a formula. You spend 5 minutes on top of this, you're going to get the answer. But basically these two formulas are going to help us understand how do we use this particular cycle. Now let's say we have so when we are in the epoch, right, we are enumerating through our batches. When we are enumerating through our batches and you are at batch number 449969, what learning rate should I use? You have to use this formula to figure out, and that LR is now going to go for SGB. Okay, so now the question comes in: how do I identify this LR min and LR max? Right, that is what we want to know. For that, we are going to ask this question: how can one estimate reasonably minimum and maximum boundary values? Now for this we are going to do something called LR range test. This is different from the test you ran last time. The test you ran last time was called LR finder, where you found the best LR which you can run your network at to get the best accuracy. That was the idea, that at that LR the network, the values were falling a lot. I also want you to realize that I also want you to realize is that when you find the best LR, let's say you found a 0.001 or 0.01, okay, this best LR is for the weights at that moment when you found this best LR. You need to realize this, right? Let me repeat it again. When you found this best LR, you found this best LR for the weights which were there at that moment. If you have changed your weights a lot, now for example Prakash also mentioned he is at 84% accuracy and stuck there, this best LR is not the best LR for this anymore, right? Now we have to find the best LR again. So you have to keep on finding a best LR again and again and again if you want to follow the best LR policy, and we can't do that. That is why we went from this to the step LR policy, where we allow the reduce LR on plateau and we keep on reducing it, right? So please remember, this best LR is only for the weights which are initialized randomly at that state only. The moment you keep on changing the best LR, it's not going to work for them. Okay, so we have to use something called LR range test in our case. What is LR range test? Run your model on several epochs, right? Run your model on several epochs while letting the learning rate increase linearly between low and the high LR values. So pick two LR values, pick let's say 0 and pick let's say 0.02. Now what you're going to do, you're going to train your network for actually epochs, several epochs, and you're going to get this kind of curve, right? So your network goes up and it actually goes down. Step size CIFAR 10. So let's see how we do it. Now CIFAR 10 has 50,000 training cycles. Now for the batch size of 100, this means the cycle is going to be 50,000 divided by 100 is 500 iterations, right? Each iteration is equal to one batch size. However, okay, 1 second. So what we are going to do after we get, so this is some other comment, I missed one, adding one image here. So when you find this kind of accuracy, what you are going to do is you are going to take the highest accuracy one. So that becomes the best, that becomes the range basically, right? So that's the max range and this is the min range. Okay. Okay. So in the LR instance, run your model for several epochs while letting the learning rate increase linearly between the low and the high values, right? So this is the low value and 0, and high LR value is going to be 0.02. So now you're going from changing your LR rate slowly. You see these are also changed on the exponential scale. So you're going to change your LR from this value to this value, and which two values are you going to pick? The high value is going to be the value at which the maximum LR was reached or maximum accuracy was reached, right? So let's say this was reached as 0.005. 50% accuracy was reached at the learning rate of 0.015. So you're going to pick your LR max as 0.015. That is going to be our max. What is going to be the minimum one? Minimum one generally is 1/8 or 1/10 of this value, right? So using this test, sometimes you're going to find that you can actually get a much better. So let us say this is your curve and this is your accuracy curve. What you're going to see that quite possible then this happens also. So you have 0, you have say 0.1, 0.2 and so on, and finally you have 0.5 here, right, and so on. So you have this kind of curve. Now so your accuracy is highest here, so you take let's say 0.55. This is going to be max LR. Min LR is going to be this divided by 10, so min is going to be 0.055, which means now I have the two lines. I have this min line which is 0.055 and we have this max line which is 0.55. So now I need to change between these, right? Okay, now let's see. Now CIFAR 10, let's take an example of CIFAR 10 to find the other parameters like the step size and cycles, how many cycles I should run this for, right? So let's look at that. So we have CIFAR which has 50,000 images. Now let us say we are picking a batch size of 100, which means 50,000 divided by 100 is equal to 500 iterations, which means each epoch is 500 iterations. But we are not interested in iterations anymore. We are interested in iterations to know that how big my cycle is. The results show that it is often slightly, so not a lot, slightly good to set the step size equal to 2 to 10 times the number of iterations. Okay, what is step size? Step size is the amount of iterations you take to go from the minimum to the maximum LR. This is min and this is max, right? So step size is the amount of iterations you're going to spend. So iteration 1, 2, 3, 4 and so on, and finally this number. How many iterations are you going to spend to reach the maximum LR? That step size generally is kept between 2 to 8 or 2 to 10 times of this iteration, right? What is iteration? Let's say I have 10,000 images and my batch size is, let's say, 1,000, which means if you divide by this, I have 10 iterations, right? So I have this as a number. So slightly good to set step size equal to 2 to 10 times the number of iterations. So let's say 2 is going to be 20 or 10 is going to be 200. Why there's a big range? Because Leslie Smith, this is from the Leslie Smith's paper itself. He found that if you set your step size equal to 2 times the iteration, or if you set your step size 8 times the iteration, 8 times is slightly better than 2 times. So there's not a lot which you're going to get, but it's still good to know of how many iterations you're going to keep. So your step size is going to be equal to, let's say, 2 times the number of iterations. So 2 times 10 into 20. So this is going to be 20 iteration, right? What is one cycle equal to? One cycle is equal to this into 2, right? Because I have to come down as well. This is our cyclic learning rate. So in cyclic learning rate, you're going to vary your values between two values. Now, why do we do that? This is something I want to discuss with you, and I want to show two graphs to you, and I want to ask you which one are you going to pick as a model. Let's say you're in deployment, right? You are about to deploy a model. I'm going to give two models. This is model A. This is the loss of model A. This is the loss of your model A, right? It goes to 99.6% of accuracy, right? And this is your model B. This model goes to 98% accuracy, right? This model goes to 99.6% accuracy, whereas this model goes to 98% accuracy. Which model are you going to deploy? I just want you to think and then tell me. Either you can comment or you can just, it's better you comment because audio is going to be slightly tricky. So model A or B, take your 1 minute and think. You want to deploy, which model are you going to deploy? Right, and the reason that is, look at what is happening in model A. Model A will give you 99.6% accuracy if image happens to fall exactly here, right? What do you mean by image falling exactly there? That I mean that image, for example, this happens a lot in face recognition. Your face is frontal, right? The face is bright enough, the lighting condition is also good, everything is good for the image, then your network is of course going to tell you 99.6%. What is happening here? Your image can be in very different varied positions and it will still give you 98% accuracy. That's the kind of model you are looking at. You do not want the state of art accuracy on the best data set, right? You want the very good accuracy on a very complicated data set. So this is something we are interested in. So please remember, that's the kind of minima we are looking at. Now, what is the difference between A and B? The minima are different. The A minima is very steep. The B minima is flatter, right? Now, how do I know that I am in this kind of minima versus this kind of minima? Let's see how this is physics literally. If I am this kind of minima, right? And let's just say, again, let's look at the values. So let's say this is 0.001, this is 0.002, this is 0.003, and this is 0.004. Right, I'm in these values right now. Now I will know if I am in this kind of minima, if let's say, and this is something like that, I'm here right now, let's say my value is here. If I give it an update of 0.001, right, I will be going from 0.02 to 0.03. I will be in this range. But if I give it a big update, if I give it an update of 0. Let's say 01, it is automatically going to jump out and come out of this, right? So we can force our network to never get stuck in such a minima. But see what is going to happen here. This is 0.001, so 0.001, this is 0.002, and so on and so on and so on and so on. So because the minima is wider. If I'm stuck here, even if you give a big value, it is still going to be stuck inside only, it is not going to come out. So we want to be in a minima where the mouth is bigger, and that is what we are trying to see from this image, that you don't want to get stuck in this kind of minima, you want to get stuck in this kind of minima even if the accuracy is low, because the chances of your image having exactly the same feature which allows you to predict this is going to be pretty low as compared to here, where you have a wider mouth for the minima where you can get stuck. So we want to get stuck in this value. How do we do that? We keep increasing our learning rate. So if we keep shuffling, we keep increasing our learning rate and bring it down, increase and bring it down, we are going to move from here to here to here to here and here to here. We are going to keep on shuffling. But if you have this kind of minima in your network, you're going to move from here to here to here to here and get then stuck here. You're just going to keep on moving in this kind of minima. You're not going to come out because that has a wider mouth. But what if it's local minima? What do we mean by we want local minima, right? We always want to be at local minima. You're saying if I'm, let's say, something like this, if I'm stuck at something like this, right? If you're stuck at something like this, for example, now let me extend this. Let's say I have something like this also, right? Now because I'm continuously changing my values, so I'm, let's say, stuck here, so I'm stuck here, stuck here, stuck here, stuck here, but I come out, then I'm come out. Once I get stuck here, there's no way I can go back, right? Because the amount of jump required for me to go from here to here is going to be pretty big, so I will never be able to go back to a higher local minima as compared to a local minima. So this jump is never going to happen. Always this jump is going to happen, right? The lower you go, you need much bigger update to be able to come back. You can only go lower. That is what we are doing through SGD also, right? It is also going to find out what is the direction of the lower direction. But they may be better minima than this one. Okay, Sanket, that is what we are saying. You have a better minima. The way you define a minima is that you have a lower loss there. We are saying that that is not how practically we want to deploy. We want to deploy at a location where even if our accuracy is slightly bad, but it is stable, right? That means that even if I'm 98% times able to tell that whether this is the same person, my accuracy is 98%, which means out of 100, for two people I'm going to do mistakes, but I am going to be efficient 98% for 98% people 100 times, which means 100 times the 100 days I'm going to recognize everyone, and my mistakes are going to be 2%. When you deploy this kind of model, your accuracy is going to be 100% if your model is able to even detect them, which means that you are going to suffer from a lot of complaint from the customer saying my model is not able to recognize, your model is not working, it is not able to identify. It's not just going to say that, because I is going to say 100 is going to say 0, right? So the failure rates here is high, the inaccuracies here is higher. So we want this kind of model which where the failure rate is pretty low, right? We can work out on something on how do we fix this 98 to something else, but we always want this kind of minimum. Does it make sense to send an army of LR finders across different locations and then take the inputs and decide on the best LR? Because that is what Google did, and it's a very expensive exercise, because as you saw here also, in case of finding this LR, we have to train for some epochs, right? We have to train for several epochs, right? CIFAR 50% accuracy, you will have to train for a large number of epochs. So that is something which is not easy to find, and we're going to see an alternative of that. Then comes one cycle. One cycle is again designed by Leslie Smith. This time, what he's saying is, look at the name of the paper: a disciplined approach to neural network hyperparameters, like what we are doing here, talking about how do I find my local minima, how do I find my minimum LR and maximum LR. He's saying a disciplined approach. How do we actually do it? Batch size, moment, and weight decay. He describes the approach to set the hyperparameters, namely learning rate, momentum, and cyclic decay, and batch size. In particular, he suggests one cycle policy to apply the learning rate. The author recommends that one cycle of learning rate of 2 steps of equal length. We choose the maximum learning rate and using the range test. What are we saying? So after, okay, let's see the progress we have made. First of all, find the best LR, and that is only for that particular weight. Then we said that okay, we have to start at LR, but we have to reduce it. We have to anneal. Then we said that we have to increase. Then Leslie Smith said that okay, there's another approach where we can actually keep our learning rate fluctuating, right? And this latest paper, which came from Leslie Smith, said that you start at low value, you end at a large value, and then you end at start at a low, then at the midpoint go at a large value, and then end at the low value again. So there is only one cycle, right? So, and we do this in, let's say, 20 epochs or number of iterations. We have to fix just one. So when we start at a low value, we are already annealing. When we keep on increasing our learning rate here in this particular fashion, we are making sure that you cannot get stuck in something like this, right? You cannot get stuck in something like this. When we increase our learning rate a lot, that means that you can only get stuck in a valley where the mouth is larger. Otherwise, you're going to just drop out of that. So it takes it takes your parameter to such low, such minima values where the mouth is larger, which means the stable value. So that's the kind of value we are interested in, right? So that is where we're interested in, and that can actually happen if you just continuously keep on increasing the learning rate to a very large learning rate. Imagine this is actually what is happening now. Imagine a valley, right? And in that valley, you shake that valley a lot, right? All the particles which are there in the valley are going to move out, but they are going to get assembled only in such valley where the mouth is larger, because I'm shaking it violently, and it can only get stuck here if the mouth is bigger. If the mouth is something like this and I'm shaking it up and down in some different directions, it's going to pop out, right? So we want a valley like that which has a broader mouth, so it can actually go deeper. So any new image which comes in has a much higher accuracy as compared to just one single high precision accuracy for that one image only. So we want to do something like this. So in one cycle policy, it recommends two steps: one up and second step we go down. And how do we find our learning rates? We use the range test, the same range test we saw here, right? This is our LR range test. This is our LR range test. How do we do this test? We run for several epochs, and in that epoch we keep on changing our learning rate. We see what is the highest accuracy we are going to get. That's the accuracy we have. We pick this particular point and we pick the minimum LR as 1/8 or 1/10 of it. Completely up to you. Now we go from the lower learning rate to higher learning rate in step 1 and back to lower learning rate in the step 2. We pick the cycle length slightly less than the total number of epochs to be trained, okay? And the last remaining iteration, we annihilate learning rate way below the lower learning rate value, or to the 100 to 110 to the 100. What do we mean here? Okay, so our curve is slightly complicated than that. So what we're going to do, we're going to start this at low LR. We're going to start at this low LR. From the low LR, we're going to go for the max LR, right? And from there, we're going to go for this low LR again. So let us pick some values. This is 0.001. This is, let's say, 0.5. We go back to 0.001. After reaching this point, we annihilate further. We further drop it down like this, right? And now this is going to be 0.0001 or 0.00001. This training is completely up to you. Now let me tell you why we use one cycle policy. We use one cycle policy for this part. Okay, this is your normal training. When you apply one cycle policy for, let's say, 20 epochs or 25 epochs, you have trained your model to a very high accuracy here already. But this is not the highest accuracy. Let us say CIFAR can go to 96% as the highest accuracy. This one cycle policy within 20-25 epochs is going to take you to 93-94%, right? This takes 200 epochs. But in 20 to 25 number of epochs, you are immediately going to go at 94% accuracy or 93% accuracy. Now you can slowly train it further, let's say for 50 further epochs, to arrive at 96% accuracy. So in the end, we have spent 50 plus 20, which is 70 epoch as compared to 200. So one cycle policy is not going to give you the astronomically high accuracy. That is not what it is designed for. It is designed to reach a higher accuracy in a short amount of time, after which you can actually annihilate your learning rate further. After which we can annihilate our learning rate further, we can go for a very small learning rate and finally fine tune it. So fine tuning is something we still have to do. The motivation behind this is that during the middle of the learning, when the learning rate is higher, the learning rate works as a regularization effect. What is regularization? Regularization is something which allows us to not get stuck at the minima, right? And that is what we have just discussed, that we will not get stuck at these kind of minima. We want to be able to be in this kind of minima where the mouth is wider and keep the network from overfitting. This helps in the network avoiding steep areas of losses and land a better flatter minima. So this is how we train. We start from a small value, let's say 0.1, we go with a high value 0.8, then we reduce it to same value, and we further annihilate our learning rate to smaller values to be able to fine tune it further. Either you have one issue or you have the other issue. Now, because our pages are long, I can't annotate them while I am in the middle, because it has a length of a page beyond which I can't go. Let's see now. So I have to test whether, thank God, okay. So I can't go more than below this. Okay, let's close this then. Edge also sucks. Okay, so we covered this. So this is what we are interested in, right? So we are saying is that we are going to increase our learning rate, and we are then going to reduce our learning rate, and finally we are going to annihilate. Now this figure started at 0.41 and we make step 41 epochs. So we took 41 epochs to reach the 0.8. We reach 0.8 here, and then make another step of 41 epochs and we go at 0.008. 0.008, there we started, right? You see this 0.8 and 0.008, it's 1/10. So lower LR is lower learning rate is not found, only the max learning rate is found using our step range, and the lower is going to be 1/8 or 1/10 of it. That's the there's a result which is like published by a different paper. There's no logic behind that. Then we make another 13 epochs to reach to 1/10 of the 0.008, which is going to be 0.008 now. So from here we go to 0.008 in the 13 epochs. Now this is where you can spend your time, right? This is where you can spend your time. Now with cyclic learning rate 0.008 to 0.8, batch size of 512, momentum 0.9, resonate 56, we got 91.3% accuracy in 95 epochs. Otherwise it takes a really long amount of time. Now, when you're using cyclic learning rate, we also implement something called cyclic momentum. In cyclic momentum, okay, so when we are in the mid stage, what exactly are we trying to do? We are trying to make sure that we are shuffling the network a lot, which means that we are adding a lot of fluctuation to it. This is exploration again, right? And we're trying to explore in such a way that we don't get stuck in the local minima. But I can get stuck at local minima if the momentum is pushing me in that direction. So we slightly reduce our momentum as we are increasing our number of iterations. So we go at 0.95 momentum. We go for a momentum at 0.8, exactly at the point where our LR is maximum, and as we are reducing our learning rate, we increase our momentum back to the same value, right? So we follow the reverse of cyclic learning rate. So if in the cyclic learning rate we are starting here and we are ending here and we are doing something like this, for the momentum we start at the high momentum, we reduce our momentum at the same point, then we increase that, and then we keep constant, right? So this is 0.95, this is 0.95, this is going to be 0.8. Now these values are sort of empirical in nature, which means that you don't have to search for it. You can actually use these values, 95, 8 and 95. These are the values which Leslie Smith and others have found in their research papers as well. Now in practice, this is very important for us. In practice, we choose two values for the momentum, 0.95 and 0.8. We cover this. Okay. With one cycle policy and cyclic momentum, I could replicate the result mentioned in the paper, where the model achieved 1.54 accuracy in 9310 iteration, while using one cycle policy with learning rate 0.08 and etc. We covered that. Okay. Now the question is, does it provide us higher accuracy in practice? Okay. It is one time during training. It is one time during training. That's correct. How momentum will push you in minima? Could you please explain later on? Just let me finish this. Okay. How momentum is pushing in local minima? This is where you are. This is where you are. Your direction is already in this direction, right? So momentum is going to further push you in this direction. That is what momentum is doing. So you want to rely less on momentum, right? And that is what we are trying to do. Okay. Right, what is momentum? Momentum is giving you a particular direction where you are already going. So if you're already going in a minima, it is going to push you further, so we reduce the effect of momentum slightly. Now does it provide us a higher accuracy in practice? Right, when I'm saying higher accuracy, I mean that with respect to the state of art, if I use one cycle policy, will I always end up with a higher accuracy? The answer to that question is no. Then the question comes in, why are we actually using one cycle policy then? It reduces the time to reach near to that accuracy. If your state of art accuracy is 98%, one cycle policy within few epochs, 20 epochs or 40 epochs, if you keep your parameters correct, will immediately take you there, very close to 98, so 97 maybe, 96 or 94 maybe. Otherwise, you would have had to spend 100 epochs, 200 epochs, 400 epochs and days to train. So this is something which helps us go there faster. And after that, again, of course, slow down my training and slowly take more number of epochs to reach there. It allows us to know if you're going right early on or not. If in the 10th epoch my accuracy is not increasing, I know there's definitely something wrong I'm doing. If my accuracy increases very slowly, right? If my accuracy increases like this, something like this, so I have to wait for these many epochs, and I have to maybe wait for, let's say this 100 epochs. I have to wait for 100 epochs to know even my network is learning or not. One cycle policy, however, would do something like this immediately. Now, if I draw a line, if I draw a line here, right, and if I draw a line for one cycle policy, you're always going to see this delta, right? This delta is always going to be there, which means one cycle policy will always be slightly less than your normal one. But now what you can do here, after you reach this particular point, now you can anneal that, now you can annihilate that, right? Now you can train at a very slow number of, and you can finally reach something like this. Maybe now you will reach. So you see, you have reduced your time, you have reduced the time to understand your model is working or not, and that is very, very crucial. Why? Because it reduces the cost of training, it reduces the time to deploy, and that is important for us. I don't want to wait for a week to realize that my network is not working, my cost of deployment is also going to be high because I'm going to be using my GPU or AWS. And you will hear a lot of stories online that one developer just use something bad and AWS bill is $100,000 or something like that. We don't want to be in ever that scenario, so we want to use one cycle policy for that. Now, there are references. I'll request you to go through these references to make sure that you understand some of the topics we have discussed. Now, one cycle policy can be applied only to SGD or is applicable to RM. Now, one cycle policy, what Leslie Smith has designed is for SGD. I also told you that we use SGD mostly for our data sets, right? Because we have large data sets. When you have small data sets, you can go with Adam. But when you have small data sets, we actually don't go for this kind of training. For small data sets, we go for, let's say, transfer learning or something else, right? So we don't actually, I don't know how to answer your question. If you are forced to use ADA, then you can use one cycle policy there also, right? So if you, this is what you are listening at, but I will not use it because I always use SGD. If this was NLP where we can use ADAM and other networks, then one cycle policy doesn't come into play because that is you have a lot of searching to you have to do a lot of search there. So I don't know where exactly to use ADAM and one cycle policy, but people don't have as high confidence as I have on SGD, so they use ADAM with one cycle policy also, so completely free. Okay, now I want to talk to you an assignment. Write a code that draw this curve without arrows. I don't want you to draw the arrow, I want you to draw the curve. So you can use Plotly, you can use any matplotlib or anything, but you have to make this, you have to basically draw this curve, right? And I don't want you to draw this curve using some OpenCV or some graphing library. This is literally a graph. So I want you to draw a graph which goes up and down and up and down. So I want you to draw this chainsaw. And how can you draw this? We saw the code already for that. This is the code we saw, so you have to replicate this code, but I will request you not to look at the code and come out with your own code. If you do that, then you will be able to implement a cyclic learning rate whenever you want. Okay, second thing, write a code which uses the new resident architecture. So I'm defining a new resident architecture here. Please look at it carefully and make sure that you understand this. I'm going to copy this and hope that I can paste it this time. Bhagwan. See, it is there in the RAM, but it is not able to pick. Okay. So I want you to write this network, and this network is for CIFAR 10, by the way. Okay. Now I want you to first write up first layer. So this is 3x3. So we have this 3x3 layer, right? And this is preparation layer. I'm calling it a preparation layer. Here the stride is 1, padding is 1. Stride 1, padding 1 for every single layer. Don't have to worry about even thinking twice on this. Followed by batch normalization, followed by ReLU. So this is followed by batch normalization, followed by ReLU. And I have 64 kernels here. So wherever you see K, that's the number of kernels, right? So this is done. After this, we start at layer number 1. Now layer number 1, this is a resonant block, so you have to make a resonant block here. Okay, what exactly are we doing here? We are doing first again a convolution by 3x3, right? Stride 1, padding 1, followed by max pooling, right? Followed by max pooling, followed by batch normalization, followed by batch normalization, followed by ReLU, followed by ReLU, right? And this kernel is 128, which means that I have used 128 kernels here. So this is where we are right now. We are in the layer number 1. Now we add the resonant block, right? So now we have our resonant block. So this takes this input and has 128 outputs, 128 outputs. So resonant is not doing anything special. Now once this is done, Once this is done, we are starting with our layer number 2. What is the layer number 2 now? Layer number 2 is going to be our 3 cross 3, but this time 256 kernels, followed by max pooling, followed by batch normalization, followed by ReLU, followed by max pooling, batch normalization, ReLU, followed by max pooling, BN, and then ReLU. Right? After this is done, after this layer is done, after this layer 2 is done, this is layer 1. Right, after this is done, we are at layer 3. We are at layer 3. Layer 3, we are again going to do the same step. So we have this 3 cross 3 with padding 1, followed by max pooling, followed by BN, followed by ReLU. But this time we have 512 kernels, and this is followed by resonate block 2. Right, so what is resonate? I'm sure this becomes X. We convolve it 2 times, right? We convolve it 2 times. Okay, why 2 times? Look at the architecture here: convolution, batch normalization, ReLU, convolution, batch normalization, ReLU, right? And then we are going to add our X and Y. We are going to add our X and Y, and after this, we are going to perform max pooling. Look at this. This is slightly different. I'm going to do max pooling with a kernel size of 4. Why the hell? What the hell is going on? Let's look at the whole thing again. Okay, this is CIFAR 10, I told you, right? So we have CIFAR 10. So CIFAR 10, 3 cross 3 slide 1 padding 1. So size of the image after this step is 32. Then slide 1 padding 1, size of the image after this step is 32. Max pooling, this becomes 16. Not changing size, not changing size, no change in size here, no change of size here also. No change of size here because slide 1 padding 1. My size has changed to 8 now. No change, no change. Now no change, max changes to 4 here. Now no change, no change, no change, no change here, no change here. Max pooling with a kernel of size 4. So the input itself is actually a kernel of size 4. Input itself is a channel of size 4, right? So we have these channels coming to this particular layer, and now we are doing a max pooling with a kernel of size 4. So basically we are going to be picking one particular pixel out from this. So we have, what is the input to this? What is the input to this max pooling? Max pooling is the input of the output of this resonant block, which is 512 channels. So after this step, I'm going to get 512 values, and I'm going to perform fully connected layer. After this fully connected layer, you're going to do from 512 to 10. Why? Because there's only one fully connected layer shown, and I have 10 classes as the output. So after that, we apply softmax. So this is the way you're going to write your network architecture. So that's the network architecture you're going to write. Second thing, you're going to use one cycle policy where you have total 24 epochs. So I have this 24 epochs. The max at epoch equal to 5. So the max value, the max LR is going to be at epoch number 5. So 0, 1, 1, 2, 3, 4, 5. So the fifth one, I have my max LR. Okay, so this is the max LR. LR min, you have to find. LR max, you have to find. You have to find what is the max LR. You have to find what is the min LR. And with that min LR, you're going to take 5 epochs to reach there. And from there, how many epochs are there? 24, which means 24 minus 5 is equals to 19. So you're going to take 19 epochs to go back to the same value, right? And you're going to use this transform. What is the transform? First is called center crop 3232. So you're going to take your 32 cross 32 CIFAR images. You're going to add a padding of 4 all across. So your image becomes 4, 4, right? 8, so 40. So your image becomes a 40 cross 40, right? So this is your 40 cross 40 image. Then you're going to do a center crop of 32 32. That means that you're going to pick this image of 32 32. Any random image, random crop. I should not return a center crop. This is a random crop. So random crop of 32 32 from the 40 cross 40. So now your image will keep on shifting, right? So your object in the image is always going to be some zigzaggy because you're selecting this. You're going to implement flip LR, basically left and right, and you're going to do a cutout of 8 cross 8. So that's the way you're going to write your model. Okay, batch size is 512. Your target accuracy is 90%. The lesser the model of your code, the lesser the marks you're going to get. So your code has to be extremely modular, which means when I ask you to paste your code for the IPython notebook, some of you are actually pasting the code of the IPython notebook, right? I don't want the code of the IPython notebook. I want the code you are writing in the IPython notebook. So some of you are opening the whole complete IPython notebook in a text file, text editor, and copying pasting the whole code. I can't undo that, right? I just need the code you're writing in your Jupyter notebooks. Now the questions which are asked in the assignment are: upload the code you use to draw your zigzag, upload the code you use to draw your zigzag, and cycle training, upload a triangle plot which was drawn using your code. So whatever code you use to draw this, I want the image of that code also. Upload the link to a GitHub copy of the collab code. So for the collab for this particular file, upload a GitHub link for the model as described in A11. Yeah, this model must be there in your folder called model, right? And I should be able to find the other models also. I should be able to find the assignment 7 model, the resonate 18 model, and any other model you've written should be there along with this model. And what is the test accuracy? So these are the questions I have asked in the assignment. Now we are breaking up for the question. So if you have any question, please let me know. Cutout of 8 cross 8 has to be applied on the padded image or the original image. It has to be applied on the final image of the. Okay. Steps are, I'm going to take 32 cross 32. I'm going to pad it with 4 cross 4, so I become 48 48. Then I'm going to do a random crop of 32 32. So this is the image I have. Now I'm going to add cutout. Right, so step 1, pad by 4. Step 2, random crop of 32. And then step 3, 8 cross 8 cutout. So we are applying this on the augmented image. What is Deepak? That is what I want you to figure out. So that is what I want to discuss in the next assignment, that why exactly are we doing this. Are we moving away from the gap in this assignment? In this assignment, yes, we are moving away from the gap. We are seeing another alternative approach where we are not using gap, but we are using something very different here. We are using a max pooling of the same size as the image. So I wanted to explore this concept, and that is what we're going to again see. In layer 3, we should add XR1 or XR2. Layer 3. In the layer 3, XR2. This should be XR2. This XR2. You can use Jitsi also for questions. If you think you have a longer question, you can ask. That is correct, Sanket. What we saw in the last, I don't say never use it because these are different approaches, right? If you're going to apply this, for example, the way you're going to find your LR, you have to run for several epochs already, right? So you're going to spend some epochs there. So you're going to take a model, you're going to train for several epochs to find the LR max. So we have already spent some epochs. Now you are going to spend time on how long should I run it, how many iterations I have to do. So when you think you have a lot of operations to do, a lot of iterations to do, you're going to go for one cycle policy. So this is a much better approach as compared to the approach we saw in the last session. Can we use NumPy to draw the graph? As long as you are writing the code, I'm okay with everything. I need you to be able to calculate that zigzag. So as long as you are doing that, perfectly fine. Replace the gap with a max filling for. Could this be introduced? Could this be to introduce? Prakash, no, that is what I want you to understand, and we are going to discuss this part in the next session, or why exactly we are doing this. So can we infer after, okay? Do we need to write our own function for cutout, or can use transform from augmented packages? You can use transform from augmented packages, and there's also inbuilt in PyTorch if you carefully see it. While using cutout, we also have option of multiple holes. Which one is better, big hole or multiple hole? I like one single hole instead of multiple hole. Multiple hole is like more like a dropout, so I don't like to rely on that. I like to rely on one single hole. So it's a preference. Uh, there is no winner or loser here. It's a preference. I prefer one single hole. Cutout 8 cross 8 means default parameters. I don't know what you mean by default parameters. Okay, I need to end the Jitsi call. If you have questions, you can continue on the chat. I have very low on battery, so it's going to die down anyways. Does one cycle LR cycle error over starter points? Yes, it does. Convolution batch normalization reloop, convolution batch normalization reloop.
The people have dialogue flow and so on. Once you go down that route, easily going to be put in the car.
Right? CBR is convolution batch normalization reloop. Yeah, I just did that. No, we don't have to. You don't have to add this annulate part. No annulation. Can we use automation for transform input by top? No, no, anything. Anything. It must be modular basically. I'm expecting you to use your own code for transformations, right? I'm not expecting you to PyTorch. I'm not expecting you to call. I'm just telling you that in your module you could have called PyTorch or you could have called an automation. Completely up to you of which model you want to follow. Just to confirm, padding to be used is 2 or 4. It is 4. In the future, we'll have a small dataset problems also. So we're going to look at that. After reaching the LR min in the descent, do we have to still annulate? No annulation. Only 24 epochs. Okay, you lost that CDR. Okay. This is 2. For one cycle LR, can we use inbuilt function or we have to write your own? You can use inbuilt function. All right, if you have any other question, you can post in the chat or Telegram. I'll take it from there. Cool, then I'll stop the stream. Have a very beautiful day.